Hello and welcome. Today we're going to talk about cosine and sine series. What's going on here, of course, is we've seen before from the heat equation that if we have Dirichlet boundaries, let's say we take the simple boundary of just zero temperature. If we have the zero temperature boundaries, then we get Fourier solutions that are of the form, the initial condition, f of x, for this sort of thing is always going to be of the form of the sum of bn sine n pi over Lx, where n goes from 1 to infinity. Okay, so as we noted here, there's no cosine term. There's only a sine terms. So what we want to understand is what's the nature of these kind of series, which we're going to call sine series. And then also, if you have a Neumann boundary condition or a no-flux boundary condition, the initial condition, f of x, was a cosine series. A0 plus the sum of n equals 1 to infinity of an cosine n pi over Lx. Okay, so in this case, this is the no-flux boundary condition, which is determined by that x equals 0 and L are both no flux, so there's no heat flux. So the derivative, the partial derivative with respect to x of the temperature is 0. So, and this, of course, right here is a cosine series. So they both played a role thus far in understanding, in characterizing initial conditions to the heat equation on a bar. So we want to understand what's the deal with Fourier series that have only sines or only cosines, and how many different functions can we represent. So far, we know how to represent f of x as a Fourier series involving both sines and cosines. N equals 1 to infinity. We know how to do this sort of thing, and in fact, and this works for all piecewise smooth functions. So the question then, of course, is, what can we approximate with only sine or cosine functions? So that's the question. And clearly this has a direct application, because we see that came out of the Dirichlet boundary problem, the zero end temperature problem, we had a sine series only. And for the no-flux boundary, where we had a zero derivative on the boundaries, we had a cosine series only. So the question is, if I pick any initial condition for f of x, can I represent this initial condition as a cosine series or only as a sine series? And the question is, yes, anything, piecewise smooth. So it turns out that the subseries involving only cosines and only sines can also represent these functions. So but there's some details that we're going to have to sort out in order to do this. So there's the setup for the problem. And so what we're going to do is just go over the theory here, and then in another video we're going to go over how to compute it for an actual example. So let's do that. All right, so some background. We know something called an odd function. And an odd function is a function such that if I have f of x, it's equal to the negative of the negative x. So what this represents is if I have a function like, say, something like this, and that's for the positive values of x. Now on the negative side, what I do is if I go to a point here, let's say, and I go to the same point on the opposite side, so this is x here, and I'll call that negative x there. All right, so it has to be that the negative x value is the negative of the original. All right, so that means if it's positive here, it has to be negative on this side, right there. So it turns out that looks like that. So essentially there's mirror images, so I should say flipped mirror images. So they're flipped about the y-axis. So that's the definition of an odd function. And an even function is similar. It's a function such that f of x evaluated at some value of x is equal to the negative value, is equal to the function evaluated at the negative value. So this is an odd function. And an even function, if I have the x-axis again, x equals 0, it'd be something similar. So I'd put it like that. What would happen is I would want the positive side there. Like that. So here, these are non-flipped. So it's a true mirror image. So in this case, of course, if I have my point x right here, we see that there's the same point on the other side at x as well. And it's not the negative, but actually just the same value on both sides. So and that's true for every point. If I take this point there and that point there, they're on opposite sides. And you see that the y values are the same for each one. So those are even functions. And of course, the classic example of an odd function is, of course, sine of x. And even the classic example of a even function, of course, is cosine of x. All right, so obviously, clearly, those are our trigonometrics that we're going to be exploiting in Fourier series. So let's understand now a little bit more about what's going on here. So let's now consider an f of x function like this that is odd. And now what I want to compute is the Fourier series. And I'll assume that it's piecewise smooth. So for this graph of this function over here that I've chosen, it's clearly true this is piecewise smooth. There's one point at x equals 0. So we'll say that's x equals L here. And there is x equals negative L here. Okay? And we'll assume it's piecewise smooth. And so there is a single discontinuity, but otherwise it's a smooth function as we've drawn it here. So we can assume it's piecewise smooth. And we want to write down a Fourier series when we know it's just going to be writing down the grand Fourier series that we've always written down before. A-n cosine n pi over L x plus b-n sine n pi over L x. All right, and then in order to compute these, we need to compute the Fourier coefficient. So what we do is A0 is equal to the inner product of 1 against the function divided by the inner product of the function 1 with itself, and that's going to be 2L down there in the denominator, and then it's going to be negative L, 2L of f of x dx. And I can break this up into two pieces, 2L, integral from 0 to L of f of x dx, and also negative L to 0 f of x dx. Now we can see from this that that now f is odd, so what I can do here, of course, is substitute u is equal to negative x, all right? And then we can get 1 over 2L integral 0 to L f of x dx. And now that means that negative u is equal to x, and du is equal to negative dx. And then we can put it all together, and actually that becomes L to 0. And then there's a negative sign there due to the negative du that we'll put on there. And then that becomes Lf of negative u du. Okay, so what we know about this now, I can take this term and do a few more things to it. We know that the function is odd. That means that what an odd function, another way to define an odd function is a function such that if I take the negative x inside of f, the negative passes through f of x. So we can see that happens there. So we're going to get a L to 0, and that negative will cancel with that negative, and we'll get f of u du. Now, of course, we see that L is a positive number, and it's bigger than 0. So what we're going to do is flip the limits of integration and end up with a 0 to L f of u du. All right, and we can see that this, of course, is identical to this term here, except for the negative sign, and so they cancel, and we're left with 0. All right, likewise, let's go do the same thing now with the an term. I'm going to have to go to a new page. So f of x is equal to, is odd, a0, which we now found out was equal to 0. And the sum of an cosine n pi over L x plus bn sine n pi over L x. N equals 1 to infinity. Okay, so now we wanted to compute the an terms, and that's going to be the inner product of cosine n pi over Lx against f itself, which is an odd function, divided by the cosine n pi over Lx with itself. All right, so I don't need to really, I'm not going to consider this calculation. I'm just going to focus on that top calculation that we've done. We've done this one very many times. We know what the value of it is. But that's going to be, so just put that ditto down there. Integral from negative L to L, cosine n pi over Lx, f of x dx. And we're going to do the same trick as we've done before. So I'm just going to take this top piece and just calculate that. I'm going to take it from 0 to L, cosine n pi over L of x, f of x, and then I'm going to add on the negative L part to 0 of cosine n pi over Lx, f of x. And we're going to do the same trick as we did before and say that we're going to say that let x equals negative u. And what we're going to end up with, if you do the same process we did with the last one, is we're going to end up with 0 to L cosine n pi over Lx. Sorry, there's a dx there, f of x dx, and it's going to be minus 0 to L of cosine n pi over Lu, because remember, cosine is an even function, right? So that means that if I put cosine of n pi over L times the negative u in there, it's going to equal cosine of n pi over Lu, because even functions absorb negative signs in their inputs. But f is an odd function, so it does not do that. And so it will project a negative sign outside, and we get f of u du. And of course, these two integrals are the same, and they cancel to create 0. And so now what we can say then is, an is equal to 0. Okay, so now we're saying anytime that f is an odd function, we conclude f, when it's an odd function, its Fourier series is a sine series. Okay, so anytime f is an odd function, the Fourier series will be a sine series. There's no ifs, ands, or buts about that. The cosine Fourier coefficients and the a0 coefficient are both 0. So we get a sine series by default. So the question then is, what can we do with that? So that's nice. So now we know that there's this restricted class of functions, odd functions, such that they always produce sine series. But let's go back to our big question then, is that if I have an initial condition for our zero-temp boundary condition, and I have a bar from 0 to L, and I have an initial condition on this, and it can be anything, but we'll assume that it's piecewise smooth. But this is over 0 and L, right? So f is not an odd function per se. I'll put an exclamation point there. So if f is anything, but it's not an odd function, because we're not even considering the other side, the negative L part, right? That's like this, not even on our radar. So what we want to do then is now define f, our initial condition, having what we call an odd extension, which we can just write f, we can even just put an O there of x, so that what we do is we define our initial condition just like before, 0 to L, and I'll just draw something interesting over here. There we go. That's our initial temperature profile for our bar. But what we'll do is we'll now expand our definition of our initial condition to include negative L's as well, and negative x values, I should say. But we're going to do the odd extension of it. Oh, I'm doing a terrible job at drawing. All right, so there's the odd extension. So call this is our odd extension. All right, so in this case, f of x, our initial condition, is going to be equal to the odd extension on the interval 0 to L, and then it'll be equal to the negative version of it on the backside there, into the negative values. So then we know then that f, the odd extension, has a nice sine series. There we go. So now we have a way of computing the initial condition. Is what we do is we just expand what we mean by our f of x by now making f of x be the odd extension over this longer interval, and we now have a way to represent our initial condition as a sine series only, which is what we needed to solve our PDE. So now one little note here. Is there something we can do with bn's? So I'm going to put a little question mark there. And it's certainly true that we have, again, bn is going to be the inner product of sine n pi over Lx with f of x all over sine n pi x over L with itself, ditto. Okay? All right, but we can write this in a really simple way. Because the function is two replicated versions, and sine functions always are odd as well, because they're also odd. What we can do is we can restrict and so if, for instance, here's if we make L, if we just think of n is equal to 1, we have the function. There it is. This is sine n pi L. That's sine, but n is equal to 1, so it's going to be pi over Lx, right? Now you notice that it's, again, this is an odd function, so it goes positive this side. There's a mirror image negative on that side. So what we could do is multiply both of these by each other, and of course you see that they're individual copies. Just like before, what we see is that's going to be negative L to L of sine n pi over Lx times f of x. We can rewrite this as 2 times the same integral from 0 to L sine n pi over Lx f of x dx. And of course we have the same inner product on the bottom. What we can do then is we can abbreviate all of this to the following coefficient, that it's really just going to be 2 over L times the integral 0 to L of sine n pi over Lx f of x dx. So that's the abbreviated notation. This is the formula we can use to calculate our bn's. So we don't have to integrate over negative L to L. We can just integrate over L from 0 to L and just multiply it by 2. And that's a nicer, just a little bit simpler formula for computing what we've had before. All right, so the next question then is, so we've talked about cosine series. And we have something like this. A0 plus the sum of n equals 1. N equals 1 to infinity of an cosine n pi over Lx. And a very similar process can be done here. So of course this is useful in no-flux boundary conditions. So we have the condition, the partial of u with respect to x evaluated at x equals 0 or L is equal to 0. And we get this sort of condition. But what we can do is, for our initial condition, we can define, just like we did for the sine series, define an even extension which I'll call Fe of x, where, again, if we draw out our curve, here's our 0, and there's our L, and there's our negative L. If this is our function f, defined on 0 to L, we can do the same thing by putting a mirror image on the other side. And in this case, once we have that even extension, we can then go that f, the even extension of f, is equal to normal f on the interval 0, sorry, I should not include 0 in there, to L. So that's the even extension. So everywhere we need our initial condition to be these values here, the even extension will cover us. But it also gives us this other half on the other side that we don't necessarily need, but we know with this thing that we can deduce, just like before, that the b ends are now 0, i.e. that the inner product of f, an even function, with sine terms is 0. And that's the statement of orthogonality. In which case, we now can conclude that fe of x is going to be equal to a0 plus the sum of an cosine n pi over L x, n equals 1 to infinity, and a0 we can write as simply as 1 over 2 L, or apologies, hold on there, 1 over L of 0 to L f of x dx. And that's because, of course, if I integrate and find the area under the curve for this half, the other half is identical. So I don't need two copies. I can just multiply it by 2. So I just get this simple result. And an is going to be equal to, will be simply, again, 2 times, because we get 2 copies, over L, an integral from 0 to L only of f of x cosine n pi over L x dx. So those are our formulae for computing the coefficients for our even extension for when we're dealing with problems of a no-flux boundary. All right, so those are our equations for our Fourier series. So thank you very much.